Recorded.
Okay, so hello everyone. So welcome to our this week Rogers Efficient AI seminar talk. And actually, this is the first talk in this semester. So very welcome to join this. And today we are very happy to have the Professor Tianlong Chen from the University of North Carolina to give us this talk. And Professor Chen is an incoming assistant professor in the computer science department at the UNC. And currently, he's a postdoc researcher at the MIT and Harvard. And Professor Chen received his PhD degree in the electrical and computer engineering at the UT Austin in 2023. And he received several prestigious fellowships like IBM, Adobe, Graduate Dean's Fellowship, and also he received the Adware Machine Learning Rising Star Award and also the Best Paper Award from the inaugural Learning on Graph conferences. And he has served the area chair in several peer-reviewed conferences. And so you may know that Professor Chen has the very wide interest in the many important areas in the machine learning and has the very in-depth contributions in several areas and published a lot of the very important works in those the prestigious machine learning and AI conferences. So now let's welcome Professor Chen to give us this very emerging talk on the MOE. Okay, Tianlong, it's your turn.
Thank you. Thanks for the nice introduction and thanks for the invitation, Professor Yuan. So I'm very happy here to present our recent efforts in the efficiency and accountability directions related to the large language models and the sparse mixture of experts. So today's topic will be demystify efficient and accountable large language model from an SMoE perspective. We all know that in the current machine learning, AI community, more and more researchers keep pushing the model size of the language model and looking for more over-parameterized models because they can achieve impressive performance on various applications like machine translation, recommendation system, art generation, and scientific discovery. One of the key reasons behind this performance is mainly about their gigantic network size. Let's zoom in a little bit. Like in 2018, Google proposed BERT model with more than 300 million parameters. At that time, it is already quite large. Like although like during 6 years development for the GPU and computing device, we are affordable to running larger models. For example, later on, OpenAI proposed GPT-3 with 175 billion parameters. Nowadays, Google and several startup companies can even scaling up the model size to the trillion level. Such kind of massive parameter counts usually requires a lot of computational cost. For example, it will burning thousands of GPUs, thousands of TPUs for thousands of hours, which means usually even for single round training for the GPT-3 level models will cost you more than $10 million. And beyond the efficiency concerns, the generalization accountability issues still exist before we can really use such language model, such AI in the practical applications. In today's talk, I want to briefly mention 2 points. The first main point will be the efficient challenges in the language model or in the large language model. So first of all, we are curious about how can we enforce some appropriate sparsity patterns in the language model or in the large language model. We know like in the traditional CNN or the transformer, even for LSTM, MLP, there are tons of sparsity algorithms. How can they be leveraged or developed in the language model scenario to enable the efficient training and inference, trimming down the memory cost and computational cost? Second goal, we actually want to take one step further. We want to consider whether we can achieve a flexible efficiency and performance trade-off respect to the resource availability without any further training. Why do we care about that? Because for the pre-trained language model or pre-trained large language model, how people will use them in the downstream applications people will further fine-tune them on the downstream collected dataset and deploy them on the platforms. However, for different platforms, they have different amount of resources, which means it can support different amount of parameter counts and can provide a different amount of inference budget. Whether we can train the model once and allow an institute trade-off, which can be dynamically adjustable for the efficiency directions and performance directions without any further cost. We term this desired property as self-scalability. Okay, let's zoom in the solutions and hope we can find some new insight in the large language model scenario. So in the last year, we actually proposed a benchmark called the sparsity macro benchmark. In that benchmark, we testify several traditional sparsity algorithms or sparse neural networks on some very challenging tasks. For example, multilingual translation, common sense reasoning, math reasoning, or even some scientific challenges like protein structure folding, prediction, etc. And we can see that if we zoom in this figure, the y-axis is accuracy, x-axis is the sparsity for the neural networks. We can see a lot of previous exist sparsity algorithms cannot generalizable to the language task, especially for the very challenging common sense reasoning language tasks. You pruning like 40% or 50% of parameters, performance will degrade significantly. Actually, we think it's a good thing. It motivates us to think about how can we develop new efficient algorithms to enable efficient inference training in the large language model scenario. Whether we can develop some new form of sparsity to encourage the efficiency. In our opinion, we think one of the most promising pipeline or framework will be the input-dependent sparse computing. So we can divide this terminology into two parts. One is input-dependent. Second one is sparse computing. Sparse computing is quite straightforward, which means during the computing, we will use sparsely activated neurons or network pieces. So what is input-dependent? Input-dependent means given different input tokens, we will select and activate a unique or associated small portion of models for the prediction. Let me give you a concrete example. So we can start from a transformer layer. Like we can take the multi-layer presumption as an example. In our this paper, we are doing the model splitting. Basically, we are splitting the MLP, a large MLP, into multiple small ones and treat each smaller MLP as an expert. For example, we have tens thousands of neurons in the large MLP. We divide it into 100 pieces, and each pieces will have 100 neurons. And we code each smaller MLP, treat it as an expert. After that, we were learning or develop a routing policy. Such routing policy will take the token embeddings as input and output as assignment. So basically, they will calculate which expert is most relevant to the given input token and assigns the input token to the most important or associated expert. So in this way, we can achieve quite good efficiency in both training and inference. Why? Because in each training iterations or inference step, only for a small portion, maybe 5% or 10% of neurons will be leveraged for computing the given token input token embedding. Okay, so it seems the problem gets solved, right? Because we already have such good input dependent sparse computing framework. So what kind of else we should worry about? However, the things is not quite straightforward and highly non-trivial, because in order to training such vanilla SMoE framework is highly challenging. There are a lot of bottlenecks and optimization artifacts arisen when we training SMoE. Let me give you two concrete examples. So the first one is representation collapse and imbalance routing. For example, let me zoom in the figures. This will be the TSNE or UMAP for the route representations extracted from the SMoE. We can see that most of the representations will have high similarity, which means they were clustered in a similar directions in a very small range. What kind of things like will happen after this representation collapse into a small region? It will lead into embarrassed routing and highly redundant expert. Let me take this figure for the illustration. So the x-axis is the training iterations or training epochs. The y-axis will be the portion of activated expert. So different color represent different expert. So you can see that along with the SMoE training, gradually the shallow like green or shallow blue expert will be more frequently activated, and around like 17 epoch, all other expert will not be used anymore, and only the shallow blue, blue, shallow green like expert will be used. What does it mean? It means all of other expert will be redundant, will be useless in the later training stage, probably will be useless in the inference. So this is not ideal because we have wasted a lot of model capacity in the SMoE pipeline. Second problem is overfitting to the number of activated experts. So for the SMoE pipeline, as we discussed in the last slides, basically for each training iterations and each inference step, given one token embedding, it will activate a fixed portion of parameters. Usually it's top 2 or top 1, which means given 10 experts, each time I will only use two of them, and across the whole training and also in the inference. And we found that in this way, the SMoE inference stage, the performance will overfit the number of activated experts, which means in the inference stage, you should keep the same amount of parameters activated for each token. If you decrease a little bit or increase a little bit, the performance will degrade. Okay, so all of these two challenges is basically will lead to one issue, the insufficient usage of model capacity, which means a lot of redundancy and a lot of parameters are not fully utilized. How can we tackle this challenge? Our solution contains two key components. The first one, we investigate the routing policy. So we are curious about whether we can learning or design a random routing policy to solve this problem. So for the random routing policy, in the expectation, it will lead to the uniform assignment, which means each expert will be equally treated equal important. Okay, let's go through the pipeline a little bit. So still start from the transformer layers, and we take the multi-layer presumption out and split it into multiple like smaller MLPs treated as expert. Then we, rather than use a learnable router, which will lead into the representation collapse, we instead use a random policy. Such a random policy will assign the tokens to the associated expert. So are there any like existing research or existing argument for the random policy? Yes, indeed. And I will give you a brief introduction. So for the there is like 2 years ago, several pioneering researchers already spell some efforts in the random policy design. First one is random hashing. Basically, they will design a predefined hashing table, and the mapping function is deterministic and random. For each given tokens, they will query the hashing table and assign it to the associated expert. The advantage is that yes, it's random, and most likely it's uniform, like a uniform activation for the different expert. The shortcoming is that it is predefined deterministic, which is highly biased on the random seed, and also like you cannot change or update later. Second one is fully random mapping. It's come from another paper called like teaming the SMoE training, etc. So such paper advocate a fully random mapping, which means for each training iteration and for each inference step, it will randomly assign the expert for the given token. So good advantage is that it's random and hopefully it's a very uniform activation for the expert. The shortcoming is that in the inference stage, it cannot give you a deterministic answer, which means maybe you inference today, the answer is correct, and maybe tomorrow's answer is wrong. So it is not like ideal case. So in our design, we leverage a very simple method. We use a random and a fixed router. So you can see that because it's random, it still can give you the randomness, and it still can try to make the assignment more diverse. Second one, it will use a fixed weights, which means it will lead to deterministic results each time. And moreover, let's think one step further. The assignment is produced by the multiplication between the router weights and input tokens. Although the router weight is fixed, however, the input token embeddings will keep improving during the data-driven training, which means along with the involved input embeddings, the assignment can still be updated and optimized accordingly. Okay, so the second key point will be the schedule for the number of activated experts. So in the traditional scenario, people will use a fixed k, which means set k equal to 2. And in our design, we design a gradually increased k in order to avoid this overfitting to the number of activated experts. And in our paper, we present more results for the schedule for the top k choices. For example, we will use some cyclic schedule, we will use some reverse schedule, we will use some multi-stage schedule, and also some warm-up plus some linear decay schedule. And ideally, and in the end, we found that the gradually increasing schedule actually perform good enough and very straightforward and simple, easy to incorporate into multiple SMoE frameworks. Okay, so what kind of result we can achieve? Whether these two proposed components can indeed solve the challenges and achieve our desired two goals. So first goal is efficiency, second goal is self-scalability. We testified on multiple pre-training dataset and also multiple downstream dataset. So the pre-training, this is a dense model performance, like have with a dropout regularization. And this is SMoE performance. The through is a random MoE. The SMoE is a learnable SMoE, which means the router is a learnable MLP. We can see that compared to the dense model, it cannot achieve like a significant performance advantage. And also the inference flops remains the same. Although the training time can be reduced a little bit. However, for our proposed SMoE dropout, we can see that we can achieve like much better performance compared to the dense model with reduced like time a little bit. It is mainly because we activate the whole like expert during the inference. If we only leverage half of the experts, we can see that we can achieve a compatible performance and much reduced inference flops and reduced like inference time. Okay, so I would say, so another more important point is that given such designed pipeline, we can enable the self-scalability as shown in the below figure. No worry, although there are a lot of curves, a lot of like numbers, I will go through together with you. Like let me zoom in one figures and give you a clear presentation. For example, take the transformer XL as an example. So y-axis is the performance. The lower, the better. The x-axis is number of parameters. Let's first look at the learnable SMoE and random SMoE. We can see that even you give it more parameter count, more budget for the computing, the performance cannot improve. The performance curve is flat. It is not ideal. And if you focus on our models, SMoE dropout, we can see that the performance will keep increasing if you given it more model parameters. For example, if you give it like a 1.0 times times power 7, the performance is here. But if you increase parameter counts budget 2 times, the inference performance can keep increasing. And one more point I need to emphasize that for the SMoE 3 curves, the yellow curve, the blue curve, and the red curve, we only training one model, and we vary the number of activated experts to produce different model variants on the different model parameter counts. And for the black curve, which means the dense model, actually each point in the figure we need to pre-train one model, which means there is 5 dots in the figures. We need to pre-train 5 separate models. So compared to the dense and compared to the SMoE, we can see that our proposed pipeline not only can achieve like overall the best performance given sufficient computings, also it can enable the self-scalability, which means it can give you a trade-off between the efficiency and the performance. And you can dynamically adjust the trade-off given the available resource budget without any further training, without any additional computing overhead. So 2 goals, efficiency and self-scalability. Also, we validate similar settings on the diverse downstream applications from the classification task, question answering task, common sense reasoning like tasks, and math reasoning tasks, etc. We can lead to similar performance and conclusions. You can see from this figure, our method, the yellow curve, can lead to a keep increasing trend if you given it allocate more model parameters or allocate more resource, more budget. Similar to keywords, efficiency and self-scalability. Okay, it seems like we already achieved 2 goals. Problem gets solved. However, unfortunately, it does not. Why? Because for the classical SMoE pipeline, they still have another significant shortcomings. Is the memory overhead. So, in our previous project, we do the model splitting and divide the large model into several pieces. In that case, it is okay for the memory because for the dense model, it also needs such kind of amount of memory. However, for another more broad, more general SMoE, people did the model construction in another way. So basically, people will duplicate the model into several copies. For example, if the dense model only have 1 expert, the vanilla way to establish SMoE will be the duplication for the expert 1. For example, I will duplicate 1,000 copies, and for each time, for my routing policy, I will still only choose the top 1 or top 2. So in this case, the inference and the training flops is still remains the same compared to the dense model. However, it will increase the model capacity, which means it will lead to a better generalization, better performance. But it at the cost of memory overhead, because you duplicate like 1,000 copies. Then we further propose two research questions. First one, can we craft a more compact SMoE model by consolidating the expert information? Second one, what is the best recipe to merge multiple experts into fewer but more knowledgeable, more generalizable, more powerful experts? In order to answer this question, like just a few months ago, we do iClear papers. It is credited to my incoming students, Ping Zhi. We actually very lucky got iClear 2024 spotlight, and we mainly focus on the SMoE immersion, try to address the memory overhead without hurting the performance. Let me go through the pipeline with you, like one pieces by one pieces. So we can see that given one SMoE, like in this figure, and then we want to first calculate the activated frequency, because we want to identify which kind of expert or which expert plays the most significant role in the performance. We call it dominant expert. And we can see that on the routing frequency or activation frequency calculation, we can find like two experts or a few experts have a higher frequency, which means it will be most frequently used in the inference stage or in the training stage. So we mark it as the dominant expert. The rest of them, which will be activated like in a smaller frequency, we regard them as non-dominant expert. Second step, we do the grouping. We want to associate different non-dominant expert to the most relevant, most closed dominant expert. So in this way, we can group all the experts into several clusters. And we can see that like for like this one, they have 3 non-dominant experts belong to this cluster. And for this one, maybe 4. After that, we will do the merging. We will merge all the experts within one cluster and only remain one expert for each cluster. And we do not treat them equally, because we already know the yellow one is dominant, is more important, and the green one or the blue one is less important. So basically, we want to inject the less significant expert knowledge into the most significant one, which is the yellow one. In order to do that, we are first doing a feature alignment to alleviate the like rotation conflict due to the feature alignment perspective. Second one, we will use the frequency to reweight each expert and do a frequency-aware expert merging, which means for the non-dominant expert, it will have very small weights to be considered in the merged model, in the merged expert. In this way, we can consolidate like a lot of like experts into a few, but more knowledgeable. Okay, so this is like almost the overall pipeline for this paper. However, there are one more additional very interesting, very insightful observation. We found that in the SMoE, if we do the model mergence, expert merging, we observe the merged expert actually appear or actually has a lower weight rank, which means it can be further compressed through some lower rank composition, etc. So let me elaborate a little bit more in this part. What did I mean? It will appear to a low rank in the weight space. We found that compared to the raw expert and the merged expert, if we do the PCA and only keep a few principal components, we found that the merged expert, they can use the same number of principal components to achieve a much lower reconstruction error. Or given the same amount of reconstruction error, the merged expert only need much more fewer or only need only a handful principal components to reconstruct the original weight space. Okay, then leveraging these two designs, we further testified on multiple dataset. We can see the figure is in order to support the reduced rank after merging. We can see that we calculate the delta change of the weight rank for the merged expert. We can see that all the curves, all the data set is below than 0 or equal to 0, which means after merging, the rank is significant, reduced. Leveraging these two design, we testify on multiple data set, including classification, question answering, reasoning task, or generation tasks. We can see that our method, the SMoE, the merged SMoE, can achieve consistently better performance compared to the dense model. And at most cases, we can achieve even better performance compared to unmerged full SMoE baseline. Compared to the second rows is first row is the dense model, which means no sparsity, no sparse computing. Second row is a full SMoE, which means vanilla SMoE without any merging. Middle two part is the baseline, like pruning baseline and the model merging baseline. And we will use the blue color to indicate the performance better than dense model. And we will use broad font to indicate the performance can surpass than full SMoE. Okay, some summarizations or takeaway. We can see that our merged SMoE can give you like 60% reductions in the memory overhead. Sometimes can even achieve slightly improved performance compared to the full MoE. And if we do the further compression, which means the MC SMoE can achieve 80% memory overhead and 20% flops reductions, and with only marginal performance drop. Okay, and I probably will stop here for half minutes or 1 minute. If anyone have questions, please ask. We can initiate some interesting, exciting discussions. But if I just want to let you know that I will also left like 5 minutes in the end for the QA. If you are free to ask now and in the end. Thanks.
Actually, I have several questions, but I will ask in the end. Yeah.
Okay, thanks. Okay, let me continue. So, given such like efficiency pipeline designs, we can enjoy inference training flops reductions, some memory overhead reductions. We can also enjoy the institute once for trade-off, given like a different downstream platform budget. How can such like efficient pipeline lead to accountability? How can we like also improve the accountability for the language model inference or large language model predictions? In order to achieve that, we borrow one tool called concept learning. So basically, given the large language models, we will first fit in some concept, and based on the concept and make the prediction. And such pipeline can not only bring you the efficiency, bring you the accountability. Later on, I will also introduce a new concept called self-debugging and self-correction, given such like accountable and efficient pipeline. But I will introduce it later. So what is concept learning? It is quite straightforward. So given one input, and it can be decomposed into several high-level concepts. For example, if I want to evaluate whether one restaurant is good or not, I probably will evaluate it into several dimensions. First reaction will be food, whether the food is good or not. Second one will be the ambience, whether the ambience is good or not. Third one probably will be the service, whether the service is good or not. So you can see that for each concept, we are learning a routing policy. Such a routing policy will activate its associated network pieces or neurons for the prediction. And after the concept predictions, we will further implement a concept bottleneck. Such a concept bottleneck will build on top of the concept SMoE, and will merge different SMoE, different concept predictions into the final evaluation. So in this way, we will know when you make a prediction, we can explain it. For example, if you evaluate the restaurant is good or not is good, then I can explain it why it's good. Maybe the food is good. Yeah. Pardon me? I think and someone ask some questions. Okay, never mind. We can left to the end. And you can see that. And first, we can evaluate why you make the prediction, whether it is because the food is good or service is good. This is the first level. Second level, we can also interpret why the model will make such behavior. It is mainly because such selected neurons, they contribute for such kind of prediction. So this is the second level for the neuron or model pieces explainability. Third one, we can also backpropagate to the input level to find out the most relevant input word associated to the concept prediction. For example, the food is good because the user comment it is excellent, robust. So therefore, the food is good. So this is our concept learning accountable pipeline built on top of the SMoE framework. Okay, so another questions arise. I would say not arise, it's always exist, is that the machine learning model cannot be perfect. It can always make mistakes. There not exist 100% accurate models for all the realistic tasks or for very challenging tasks. So how should we do if machine learning model is not perfect? So ideally, we hope the machine learning model can evolve by itself, right? So although currently, we will do some manually designs, we will further fine-tune the model, use some additional carefully designed prompt, use some retrieval augmented generation techniques to assist the language model, large language model inference. Or we can also design some human in loop, absorb some human feedback to improve prediction. However, all of them is not ideal, right? And in the future, we hope we can save the human more time. We want to the machine learning model can be more intelligent, which means it can do the self-debugging and do self-improvement. What do I mean self-debugging? Which means the machine learning model will diagnostic its behavior by itself and identify the potential risk, potential errors. Then the model can also improve itself by adjust some model parameters, adjust some input. So we call it the metacognition intervention. So metacognitive intervention, as I mentioned, it contains two parts. First is the self-diagnostic. So in our pipeline, we will monitoring the routing policy assignment. If the routing policy assignment and the concept assignment is very confident, which means the model tells us that, and for sure, I will choose this expert for the prediction. So I probably will trust the model. However, if the model is unconfident, which means the model tells us it seems expert one is good, Expert 2 is also good. Okay, probably expert 7 can also work. In this case, there exists a lot of uncertainty. There exists a lot of possibility for different expert. Then we probably should not trust the machine learning model. Even itself cannot trust this answer, right? So in this case, we will activate the second step called self-improving. So in the self-improving, a lot of techniques can be leveraged. For example, we can do some model editing, or we have like a 102 SML paper mainly focus on some model editing, basically manipulate several neurons to improve the reasoning accuracy to address the hallucination. We can also do some unlearning to unlearning some harmful data point. We can also do some fine tuning, like instruction tuning, like some alignment tuning, etc. All of such kind of method requires additional training. And in our pipeline, we leverage our previous work to enable some training-free self-improving method. We call it like dynamic expert allocation. It's very straightforward. If the concept prediction have high uncertainty, we will allocate more expert as indicated in the red box for the inference. It is like sounds very simple, but it's highly non-trivial because it requires the model pipeline should have the self-scalability, right? Because in over the first half of the presentation of today's talk, we show that most of SMoE, even you give it more expert, more model parameters, the performance cannot improve, sometimes can even degrade. Only if you develop the self-scalability for the pipeline, then in this case, you can allocate more parameters and can expect a better generalization ability. Okay, so let me give you some takeaways for these designs. So first one, we need metacognition for language model intervention because we do not do the human intervention each time. We hope the model can involve debugging by itself. How should we do that? First, we should do some monitoring. We should monitoring whether there are some anomaly patterns in the prediction or in the assignment. Second one, whenever we identify one error, what should we do? For sure, we want to some very efficient manner because usually it will happen at the inference time. The model is already deployed on the resource-constrained downstream platforms. We do not have any additional resource budget for further training or retraining. We hope it is training-free. So thanks for the self-scalability for the SMoE pipeline. We can use some directly allocate more parameters, more expert to improve the generalization. Third one, how can we understand the intervention? Because we do the concept level modularized SMoE training, we can backtracking the prediction into concept level, into network module neuron level, even for the input level, etc. Some numerical evaluation. Although there are a lot of numbers, no worries. I will give you some summarization and highlight to save you some energy. So this is two data set and pre-intervention and post-intervention. And this is like GPT-4, prompting method or fine-tuning method or some classical intervention method. Also compare with traditional concept learning pipeline. Our method can achieve consistent and better performance given the assist from the SMoE and the metacognition intervention. And the performance improvement is usually like 5% or 6% in the reasoning task. Is very significant. Okay, so in the last, I want to show you one case study. So because I show you a lot of numerical results, numerical observations, it's maybe still not concrete enough. So before I end up this talk, I want to show you a real case study. So in this case study, we want to evaluate whether a movie is good or not. And we will first do the concept level learning to evaluate whether the emotion arousal is good, the acting is good, the storyline, whether it's good or not good. And if we directly do the concept learning with SMoE, sometimes it will lead to incorrect answer. For example, you can see that the first row is ground truth. So the emotion is good, acting is just so-so, storyline is just so-so, the cinematography is good, and the movie overall is good, it's quite popular. However, for the vanilla SMoE training, it can make some mistakes on some concept learning. So for example, the cinematographics is predicted wrong, and it is have very high uncertainty. It will lead to the final evaluation as a wrong prediction. We didn't do any like manual intervention. We let the model can do self-debugging, self-improvement, which means do the metacognitive intervention. And we found that it can correct the predictions for the cinematography evaluation by allocating a few more experts, and it will lead to the final predictions from wrong to correct. So this is why in the last figure we see that the performance after metacognition interventions can be dramatically improved, sometimes 50% or 6% performance improvement. Thank you, everyone. And in the end, I want to express my deep gratitude to all my amazing collaborators. And thanks for your listening. Thanks for your time. Any questions?
Thank you very much, Tianlong. So very wonderful talk. Actually, I have several questions to ask, but first leave the time for the opportunity for our speakers. So you can either unmute yourself or you can input your question in the chat box.
Thanks.
I think we have some questions in the chat box. So Tianlong, can you see those questions in the chat box?
Yes. Okay, I will read it out in case everyone can synchronize in the same page. So I think Chen Yang asked, first question, with performance and flaws in mind, do you think it's completely feasible to only use one expert to represent all experts? Any suggestion for this? Thanks. Actually, it's a very great question. So because a lot of current news, right, and hot discussions in Twitter, all of them indicate there are huge redundancy in the expert. So for sure, like people should merge or prune the SMoE. However, they have like one trade-off. So if you prune everything into one expert or merge everything into one expert and fix it, so what do you lose? You lose the input-dependent computing. You lose the input-dependent flexibility. Although like it will do the memory saving and flop saving, even running time saving a lot dramatically, but the performance is limited. We testified on several NLP benchmarks with the language model, large language model based SMoE. But there is another one possibility. So it's one papers in the ACL last year, they do 1 year or 2 years ago, they do task specific pruning. Although you will still keep only one expert, but such one expert is input dependent, which means given this one, like given like this task, we will like leverage this expert, and given another task, we will leverage another task. In this case, it still can maintain quite good performance. Okay, so Chen Yang asked a second question. So if my answer is not like answer your questions, not solve your confusions, please welcome to follow up on your question. Thank you. So the second question Chen Yang asked is that as you guys open source code, on top of that, are you guys going to open source code for hyperparameter for the trainings like learning rate and specific task and batch size? Thanks. Great questions. Actually, it is a very good question. Actually, we actually prepared a benchmark work in the SMR submission, and we will archive it soon, like maybe next week. So in that papers, we do very detailed like ablation and hyperparameter like studies for learning rate, for different tasks, for benchmark, for batch size, for weight decay, for policy designs, for the SMoE training. And of course, we will also like provide some emergent hyperparameters in our like GitHub repository. Please welcome to follow up like with an email or some like message in the LinkedIn. We can chat more later on this open source part. Thanks. Okay, I think Bojian asked one more question. How do you define or separate the expert in terms of the model layers or parameters? How do you define also? Oh, okay. So basically there are like 2 to 3 ways. So in the papers I present today, we will do the model splitting, basically start from a dense layer, split into multiple pieces, and we do it evenly. For example, 1,000 neuron, 10 pieces. Each neuron will be each expert will be 100 pieces. You can directly separate it evenly. And sorry for that. There is another work called model fiction, like 1 or 2 years ago. They will do some learning, try to learning the parameter group as expert. And the third like trend is vanilla SMoE designs or a lot of current SMoE designs. They will do the duplication. So start from MLP will duplicate like 1,000 copies. And for the most recent SMoE for sparse scaling works, basically they will like do some aggregation. For example, giving you 10 dense model, they will bring all the MLP from 10 dense model together to form the initial structure for SMoE model. This is like some merge techniques. Okay, so Jin Qi asked one question. Can we compress MOE into a dense model through knowledge distillation to improve the model efficiency? Thanks. Excellent question. So in our last year, I clear 2023, like the SMoE dropout paper, we actually provide some results for the knowledge distillation. We see that distillate from like more other experts or so now distillation can indeed help the SMoE training and lead to a better performance. And we also provide some results in the MC SMoE, so emergent SMoE papers. But we didn't do a very comprehensive, very holistic study. I think it is a very interesting open questions. I know like a few group spend some efforts in these directions. We can chat offline if you are interested in the knowledge distillation part for the SMoE. Okay, Yu Gong asked one more question. Are there any hardware research opportunity in the SMoE schedule? Thanks, excellent questions. So nowadays there are a lot of like large language model like code designs or system designs. For example, there are some like power infer, etc. We also have like one newspaper like H2O or Flex Genes or streaming attention, etc. All of them like discussing the language models by leveraging the sparse neurons, sparse attentions, or attention approximations for the speed up and benefits for the hardware. However, I don't think there are any existing works to specifically co-design SMoE and hardware, although there are some like parallel computing pipelines for the SMoE. I think there are huge opportunities in the co-design for the SMoE pipeline in the hardware perspectives, because you can see that most of the expert in the SMoE will not be used like in each inference step, which means a lot of model parameters or model expert can be offload to the from GPU to like CPU memory, or even to the storage SSD memory, right? So currently we have some ongoing project. We want to like running the 66 or even 100 billion parameter SMoE in one GPU, one like 16 gigabytes GPU, like one 3090 Ti GPUs. It seems impossible, but when we involve in storage computing, when we offload redundant, offload insignificant parameters, insignificant expert, everything can become feasible. So I'm very excited about these directions, especially in the MOE software and hardware co-design. Okay, so is there a paper related to this talk? Yes, there's two papers I showed in the slide, but welcome to follow up email. I can send you the reference related to the content in this talk. Want to ask a question? Oh, thanks, Pan, for sharing this paper. Thanks, everyone. Thanks for super exciting questions. Okay, still one more question. Some mechanism of SMO is quite similar to the example learning. For later, it requires a diversity of individuals. In MOE, does it also have the requirement, the diversity of experts? Thanks. Thanks for the question. Honestly speaking, today's talk mainly cover one key challenge in the SMOE, which is redundancy and the imbalance routing. So it's another famous challenge or notorious bottlenecks in the SMOE. It's called specialization for the SMOE. So ideally, a well-trained SMOE, we hope different experts can deal with different pieces of knowledge, which means different experts will be specialized to deal with a group of knowledge learning or a group of prediction, a group of modeling. So it will naturally lead to diversity because different experts deal with different knowledge, right? And but diversity will not necessarily lead to specialization. And such kind of concept, specialization, or such kind of goals are not very well defined or well studied in current SMOE literature. It's still an open challenge and open question. And at least me and a lot of teams are still spend a lot of efforts in this direction. Welcome further discussions offline. Is there any applications of MOE in the vision paper? Yes. There is the first vision MOE is from Google 2 to 3 years ago. And I used to work with my previous PhD advisor, Professor Atlas Wang in the UT Austin. We also published 2 to 3 vision MOEs in different scenarios. Welcome any follow-up emails. I can share you the reference. Thank you.
So is some other questions from the audience?
Yes, I have a question. Is this SMOE is it for general purpose? At the beginning you mentioned training large data sets training is very, very sort of computation power demanding. And now your method propose sort of much more, you can use a smaller number, is that right? But my question is this model for general just like ChatGPT such same way or more specific?
Thanks for the question. So I would say this will be a machine learning pipeline, machine learning algorithm. The application is not limited. It is a more general framework. So I can give you a few examples. There are SMOEs in the vision task, in the language tasks, and there are also SMOE works in the medical domains. We in this year's CPR, and we got a very good feedback. We developed some customized SMOE pipeline for cancer prognostics. And in the cancer prognostics, it also, of course, it have its own unique challenges. But we we can also leverage some design philosophies from general SMoE pipeline to facilitate the performance of cancer prognostics. So overall, it is a more general algorithm, general pipeline. Thanks.
Thank you. During your talk, actually, I had an idea coming up. I feel like artificial intelligence, we probably need to develop a more specific application, like, say, for pharmaceutical application. Okay, I'll just give you an example, okay? And something for languages, this kind of stuff, and particular for scientific and manufacture, those part application, it's already very successful. Those part does not require huge amount of data to train it, actually. Is that right?
So actually, I want to point out another directions also related to the SMoE. There are recent papers, 2 to 3 papers called a mixture of RORA. I also have one paper just on the archive with Google. We do like PEFT, parameter efficient tuning, but make it be MoE structure. It will also inherent the data efficient training, few shot learning ability, but can have like more capabilities for the reasoning and the benefits from the MoE. Did I answer your question?
Sorry, your self-scaling, that part, and does it include like, if you have new information? See, I encountered this ChatGPT keep saying, oh, this I was trained that this data is not not there. So when we ask something new, said no, I don't have this capability to do that. So do you integrate something new? Basically, I assume your self-scaling can do such thing. Anything not in training the part, you can somehow you can integrate that.
Thanks for comments. So in the current pipeline, the self-scaling mainly emphasize how to fully leverage the model capacity. In the single model, we actually did not consider additional knowledges. But you are right, there are multiple ways to integrate the additional knowledges. One example will be retrieval augmented generation or prediction. In that case, we can incorporate some retrieval techniques and search the related knowledge or content from existing database, vector database, knowledge database, or online to help the downstream task or the help the prediction or the reasoning.
Thank you.
Thanks for the comments.
Is there some other questions from the audience? So if no more questions, so I have a series of questions to ask Tianlong. Yeah.
Oh, please, thanks.
So first, so I think also another audience wants to ask similar questions about the splitting the model. So you mentioned that there's 3 or 4 ways to prepare a MoE, right? So I was wondering, I know what is kind of mainstream and or is that kind of just the end of either of them have kind of there are specific pros and cons for the kind of structure and splitting?
Thanks. So, honestly speaking, I think current a lot of academia research, probably all of them are very rich. Basically, they are considered building MoE by duplications MLP. So, for example, like in the beginning, MLP have like 1,000 neurons. So they will duplicate it like into 100 copies. So we will have like 100,000 of neurons. So this is the vanilla way and the most popular way to build a MoE structure in the current research in the academia. So I'm saying maybe because all of them are very rich. And in the another trend for the efficient purpose to the model splitting, I think there is only 2 trends. First one is do evenly splitting. And when we evenly split the neurons, we need to train from scratch. We need to give it a period of training to help it can fit well for the training distribution. The second trend, maybe it can start from a pre-trained model, do not need a training from scratch, is strategically grouping the related neurons into one expert and separate them into several clusters. So there is like pros and cons. So for the first one, it's simple. Do not need any further efforts. But the shortcoming is that you probably need to train from scratch, need additional training to allow it to have a good feeding. Second one, you need a lot of efforts to grouping the neurons according to their similarity. You need to go through a lot of training samples, calculate its activation, find out which neurons will be co-activated for most of data samples. Then you probably have a high chance can group them together to form up a new expert. So advantage is most of the time you do not need a lot of additional training. So performance is quite good. The shortcoming is that you need a lot of efforts to design how to group it and how to create the different expert. Yeah. Did I answer this question?
Yeah. So I have 4 questions that, so you mentioned that like we can duplicate, very straightforward duplicate MLP, right? So they share a same multi-head attention, right? And then we have the different.
Yes.
So I was wondering, so is there any possibility that we have kind of the many multi-head attention but share the single MLP?
Yes. So honestly speaking, until now, they probably have like around 10 papers focused on the multi-head attention design and the related design about the SMoE. So they have like 2 to 3 trend. First trend, they will also do the MLP MOE within the multi-head attention module, because within multi-head attention module, there are still like 3 to 4 MLP. You can still do vanilla MLP MOE. First one. Second one, they will treat the whole attention head as expert, or whole multi-head attention head as expert, and duplicate multiple attention head. Third one, they will do some mixture of vector, and such vectors is MOE structure, and each vector will be multiplied in the QKV like vectors within the multi-head attention modules. And for sure, like different papers advocate the advantage for different trend. Yeah, honestly speaking, my previous work mainly follows first 2 trend in the multimodal multitask learning scenario. It gives us a quite good performance. Thanks.
So it seems that right now, so the architecture choice has not converged yet. So right now, many different alternatives can still compete with each other. Right?
Yes, exactly. Thanks. And also different like architecture can perform quite different in different scenarios, like especially for single modality, single task training, and in multi-modality, multitask training, we see the mixture of attention especially benefits a lot in the multi-modality integration, multi-modality learning, etc. Thanks.
Okay. So I think for kind of complete versions, that so we just have the multiple MHA and the multiple FFN, and actually we have kind of two routing network, right?
Yes.
For 2 sides.
Yes, exactly. Yes, there are also like 1 or 2 pioneering work try to design in this way. Yeah.
Okay, I see. And another question I think one audience also asked, but I want just to have some follow that. So as I know that you also mentioned that you and other researchers has also applied the SMoE idea to the computer vision, and so I would like to listen to your insight about the difference or your observation when apply the MOE concept to the NLP and computer vision. Because for NLP, we know that actually I think naturally it has a lot of the downstream task, right? And I think that is quite natural that we have the different experts to be in charge of the different tasks, downstream tasks. But for the computer vision, I think the scenario is a little bit different.
Yes, because it have like less downstream tasks. Actually, I can share like one very interesting figures from my another talk. Is about vision. It mentioned a little bit about the vision SMoE. Okay, I didn't. Okay, yeah, I found it. It here. Let me open it. Open these slides. Yes, and let me reshare my screen. Wait a moment. Yes, here. Let me reshare my screen. Yeah, can you see my screen? Oh, it's still loading? Yes, right now. So we actually do some like vision MOE. So I try to answer your question from two ways. First way, what is difference between vision MOE and language MOE? I think there are a lot of very subtle designs, subtle design difference. One very interesting point is that for visual MOE, usually the shallow layers should not be branched. So because in the vision, the shallow layers usually captures like a hawk, the color features or the gradient features from the raw image. And in the later layers, they will do a more like semantic learning. So for the shallow layers, such features like a hawk, like colors usually be shared across different images or different visual inputs, which means in the first few layers, we do not need to use MOE. We do not need to branch like input dependent or like image dependent model expert. And if you inject MOE in the shallow layers, it usually will lead to worse performance. And in the language perspective, because there are no any like shallow feature learning phenomena in language modeling, so usually we will put like SMoE in each layer or every 2 layers for the language model or large language models. So this is the first one. Second one, like what do we expect it in the vision domain? What do we want to see in the vision domain? First one, I think is still first point is still valuable is multimodal multitask learning. You can see that we actually deal with like 5 to 6 like modalities for the dense prediction, segmentation, instance segmentation, etc. And in this paper, we do some hardware co-design, and we can see that you can see the SME pipeline can lead to significant energy efficiency and running time efficiency. Second one, what we expected? We actually expected like a higher specialization capabilities for the SMoE in the vision task. You can see from this figure, we do a SMoE for the image classification, detection, and segmentation. Interestingly, we found that the expert learning appears like very exciting like specialization phenomena. For example, for the classification, we see there are some 1 or 2 experts only deal with the background for the image, and for the object, it will leverage more diverse expert. Each color indicate one different like expert. And in the detection and the segmentation task, it is also very interesting. You can see that the object, the animal age, and the content for the object, and also the background, and also for some horizontal lines and special like lines in the background in the foreground, it will activate different group of expert. So it will give us a lot of insight in the explainability and further model editing for the AI pipeline, AI systems. Did I answer your question?
Yeah. Thank you very much.
Thanks.
Yeah, I think that is all my questions. And is there any other questions from our audience? Okay, so we have very warm discussion today, and again, thank Tianlong, thank you so much for this very informative and excellent talk, and also thank everyone to attend our today's seminar, and see you next week. And Tianlong, thank you so much.
Thank you, Professor Yuan, for the invitation. Thanks for like sharing such good opportunities. Thanks everyone for listening. Thanks.
Thank you. Enjoy your trip to China and look forward to meeting in person again in the future.
Thanks. Yeah, hope so.
Thank you.
Bye. Have a good day.
Thank you. Bye.
Bye.